Okay, everybody. Hi, and welcome back to another BTSS seminar. We're very happy to have Francisco today. Let me thank Francisco for joining us and Enzo as well for acting as a panelist, discussant, call it as you like. And so the rules of the game are the usual ones. We go for around an hour with Francisco's presentation, then we turn the recording off, and then we have an informal chat about the paper. Francisco, is all yours.
Well, thank you, and thanks for the introduction. Pleasure to be here. I'm going to talk about a score-driven filter for, say, regression models with time-varying parameters when there are endogenous regressors. This is joint work with Noah Stegenhaus, a PhD student of mine, um, done at VU University in Amsterdam, where I do my own research. So the plan, I think, for the talk is to start with a recap. So an introduction in the form of a recap of, say, regression with endogenous variables and instrumental variable regression. So I'm a bit afraid that um, for those familiar with IV, this will be quite obvious, maybe too simplistic of a recap. The same thing applies for a recap on score filters. It's really just the basic idea. Those that are already familiar with score filters might be a bit too simple, but well, once we're done with that, and we are sure that everyone is on board, I then essentially put the two things together. Right, consider a regression with endogenous regressors where IV is useful to address that endogeneity, right? And where we use a score filter to address the fact that the beta in the regression might be time varying. We do look at a very simple example with a single regressor, just to go through the basics of what we think is key here. Um, I'll go through the highlights of the asymptotic results. They're in many ways quite standard once one combines IV and score filtering. So in that sense, no big surprises there. Um, and then we look together at some simulation study results and two simple applications where where the endogeneity and the time variation in the parameter turn out to be relevant. Well, let me just go ahead with that introduction, if I may. Um, Exogeneity, endogeneity, right? So what is the whole story? Just as a recap, again, for those familiar with it, this is just the basics. If anyone is not familiar, well, then this is the moment to brush up at least. Um, so when we take a simple linear regression model, right? I want to regress y on x. Well, there's several ways of approaching consistency here, but one possible way, right, is to, if we think of a least squares estimator for beta, is to actually look at the formula for the least squares estimator and figure out that we need a few conditions, or that we at least know of a number of sufficient conditions that will ensure consistency. And these conditions are typically that the model is correctly specified, so that YT is actually kind of generated by this equation. So this is the data generating process for Y, as it's stated here. We need this exogeneity condition on the regressor so that the expected value of the error term conditional on the regressor is 0. And then we need kind of the data to satisfy laws of large numbers, essentially. So it's either IID or stationary, right? Weakly stationary or strictly stationary and ergodic, something like that, and has enough moments such that we can apply laws of large numbers and conclude that the estimator is consistent to that beta. Um, and the argument, just as a quick recap, right? Can take the formula. If the model is correctly specified, I can actually substitute yt for beta xt plus epsilon because, well, we just said that that's y. That's what y is equal to, right? And of course, I can rewrite this as beta plus a remainder term. And now we can argue that this remainder term vanishes, applying a law of large numbers to this average in the numerator and the average in the denominator, if we can then argue that the expected value of xt times epsilon t is zero, which is the case precisely when the exogeneity condition is met, since the expected value of xt times epsilon t, just applying a law of total expectations, can be set to zero, right? So then we conclude, oh, the remainder term vanishes. So beta hat converges to beta, right? So that is what we've been familiar with for a long time. Of course, what happens when the exogeneity condition fails is that the remainder term doesn't vanish. So somehow beta hat t, the least squares estimator here, converges in probability, or almost surely, depending on the proof, to beta plus a bias term, let's call it. And as a recap, exogeneity may fail, so we may have endogeneity for multiple reasons. Simultaneity, so when y, so when x, let's say, causes y and y causes x, simultaneity generates endogeneity. Omitted variables, right? When I'm missing some variables that are actually correlated with x, we have endogeneity, and we results in a bias. Functional form misspecification, observation errors. Well, there's a host of other reasons that can lead kind of to the exogeneity condition failing, and then beta hat converging to a limit quantity, which is beta plus a remainder term. Well, possible solutions to these, apart from the obvious, like, well, if there's omitted variables, why don't you try to add all the relevant variables that are correlated with regressors, right? Or functional form misspecification, well, just try to make it correct. But apart from trying to address things directly when that is impossible, either because I don't have access to certain variables or because that functional form might be too complex, then well, there's several methods in the literature that can alleviate or address a number of these issues, such as diff and diff, regression discontinuity design, synthetic controls, instrumental variables, all kind of known also in their causal data science, causal econometrics, statistics literature. Right, so we are going to approach this by sticking to the last one, to instrumental variables, right? So instrumental variables introduced already a long time ago in a, maybe not all of you are aware of that. So this was a treatise on the production, supply, and demand market for butter and its derivatives. So completely unrelated, and it contained an appendix where an argument was made for how instrumental variables could be used in estimating the supply and demand equations for the market for butter in the United States. And our understanding is that the father wrote the treatise, and the son, which was a well-known statistician, probably wrote the appendix, but the work was published under the name of his father. Well, in any case, instrumental variables widely applied, as we know, in economics, finance, business, and other areas. Of course, typically the main challenge with instrumental variables is selecting good instruments. So I think in any IV application, like the ones we're going to look at, the question always comes up of, are these instruments really good? Are they strong instruments? How do you ensure that they're valid instruments, they have the right properties? But putting that aside, as a matter of principle, instrumental variables can be used to address to eliminate that in bias created by endogeneity, right? So if we take here a very simple example of a yt that depends not only on x, but also on another variable, ht. But, well, unfortunately, I'm not aware of this, say, or I cannot use ht for some reason. And so I run the regression of y on x, omitting age, and crucially, age is correlated with x. So when I run this regression, well, as we all know, this error term now contains age inside essentially. And so I'm left, this all results in beta hat converging to beta plus a term that depends on that covariance between the regressor X and the omitted regressor age. And well, that's the omitted variable bias. Of course, one can address this using IV. And the steps, just as a recap, right, are the usual ones. I find an instrument Z that is helpful in explaining X, but crucially, that is uncorrelated with the error term, right? And well, essentially by doing that, I run this regression, use the predicted X when I regress Y on X, and out of this comes an estimator that now converges to beta because essentially the error term is now uncorrelated with X hat. It's essentially the idea. That was the recap on endogeneity and how IV can address this. Bit of a recap on time varying parameters, and then we combine the two. Again, that's the whole idea. So, well, time varying parameter models are also very much used in econometrics and statistics and other fields. I think examples, most famous examples that come to mind immediately are, for example, Garch models, so models for time varying conditional volatilities, or conditional time varying mean models, right? So models for time varying conditional means. But of course, here today we'll be looking a bit at a regression model that has a time varying beta, so that will be the context, right? Well, in the presence, or if one is suspicious that the beta is indeed time varying, there's many ways one can try to address this. One can, for example, perform a regression on a rolling window to try to accommodate for the fact that the beta is changing over time, and hence only more recent observations might be relevant to estimate beta. One can also use filtering techniques like Kalman filters and its derivatives, say. And there's quite a few out there. The one that we will discuss today is score-driven filters. So we will apply a score-driven filter to try to keep track of that time-varying beta t, essentially. Score-driven filters were introduced about 10 years ago, and over time found their way into applications in all sorts of different models, from models in finance to those maybe more used in macroeconomics, spatial models. Well, there's all sorts of variants of score-driven filters out there. I think what makes them most interesting is the fact that they can be quite simple and intuitive in the way uh, you specify their updating equation, say, you specify the filtering equation. Um, and in that sense, it makes them easy and fun and intuitive to use. Um, Over the years, we've also derived some interesting properties, kind of giving some assurance that um, they have desirable properties as filters as well. So the idea for a score filter for a regression like this with a time varying beta would be to, well, take a density for the error term and then say, why don't we update the time varying parameter essentially in this way as a step in the steepest ascent direction, right? As in terms of the likelihood. So why don't we essentially take the previous value of beta, right? And then with the new incoming data, yt and xt, we update beta to improve the likelihood. So in the direction of the Jacobian, of the derivative of the likelihood with respect to beta, a bit like one does in a Newton step, right? Rather than starting only from the previous beta and stepping in that direction, we have some additional kind of decay parameters, gamma and intercept there and alpha. There's an argument for why these can be interesting if you're trying to track stochastic time varying betas. But overall, that's the idea. So this ST that we call the score is then the derivative of the log likelihood contribution with respect to beta. And we use that derivative kind of to make sure that at each step we're updating beta, say up or down, in such a way as to improve, right, the likelihood according to this latest likelihood contribution. That's essentially it. So, well, for example, for a Gaussian density, the update of beta will look something like this, right? So this is the derivative of the log likelihood contribution with respect to beta. And other papers have proposed other updates of the score type, I mean, for time varying betas, either because they're considering, for example, other densities other than the Gaussian, right? If you use a different density, you get a different update. That's essentially how score filters work. Or also other twists and turns as is considered in these two other papers that I mentioned here. But the idea is that one. The idea is very simple, actually. And, well, we will try now to use a score filter in a setting precisely where there is endogeneity. So I have to figure out a way of combining it with IV. And, well, with that in mind, I essentially turn to the model that we propose in this paper, or the score filter that we propose in this paper. So what do we have? We have a time varying regression, yt. We want to regress it on x, but there's a time varying parameter beta. Now, how do we filter that beta when there is endogeneity? So when the expected value of epsilon t conditional on xt is not 0, so the exogeneity condition is failing. Well, the score-driven filter that we propose is this one, which is a kind of two-step IV procedure where we first use an instrument Z, right? We regress X on Z, and then we plug in the error term. By the way, that's a different way of doing IV that I did not explain before, I realize now. So rather than using the predicted X in the second step equation, we can also just predict the error, plug in the error term of the first equation on the second when doing IV to solve the bias problem. That's actually the approach we take here. And I must say, we take that approach because the first one did not entirely work. And to be perfectly honest, I don't remember anymore why exactly, what kind of challenge we were getting. But I do remember quite clearly that there were some challenges and that this formulation just worked best. So, right, this is the context. We're regressing XT on a valid instrument ZT. We then take that residual term and plug it in the regression equation that which has the time varying beta that we're interested in, right? So focus here is on filtering that time varying beta. And well, if you then just take, say, a Gaussian density and write the score update, you get this precisely. This is what you get, where that is just the U hat is just the residual from the first term regression, right? And now, so the idea is quite simple. In a sense, there was, as I said, it didn't work right away, which was surprising, but I don't remember anymore what the challenges were that we were finding, but I remember there were challenges with this formulation of IV, it works. And then it was a matter of kind of figuring out, is the theory also kind of entirely fine or not? Does it work in an application, simulations? And well, as it turns out, over time, all the pieces of the puzzle got put together. And indeed, this updating equation will keep track of that correctly of the beta, even though endogeneity is present. Of course, when ZT is a valid, good instrument. When it is not, then it won't work so well. But right, we kind of the characteristics that we've seen for OLS with IV carry over for this time varying parameter case. And right, I'll take just a few minutes to go through the asymptotic properties. I forgot to ask actually if there's supposed to if there are questions throughout the presentation or only at the end. There are, I see, then I will ask if anyone has questions at this stage or if we should wait.
People usually just unmute, so don't worry.
I have a question. Can you vary pi in the reduced form equation?
That's a very good question. I'm pretty sure you can. So there's for sure now various extensions to consider. The pi also being time varying and such, right? We have not gone through the derivations. So when I say I'm pretty sure you can, it's just my intuition that you would find a way once you argue that you converge to the right pi of then bringing this back to the first equation also in some valid sense. But it's not that we have tried it yet, I must say. All right, I'll just go ahead then and look at the asymptotic properties. Maybe a bit like the recap. For those of you familiar with asymptotic properties of score filters, I don't think there's any surprises here. Pretty standard stuff. For those of you maybe less familiar, let me go a bit through it. It can be somewhat interesting. So one of the things one has to make sure that it holds is filter invertibility. Filter invertibility is a condition essentially, or the contraction condition that ensures filter invertibility, essentially a condition that ensures that the initialization of the filter is forgotten. So we don't know beta t, right? Beta t is a time varying parameter. It's a no. We don't know what it is. We have to come up with a starting value because, right, as we saw, the updating equation starts always from a previous value. So I have to figure out some starting beta 1, and then I can apply for the first time my update, and then at any time t, I update it again and again, right? But I need an initialization, and that initialization is, say, almost surely incorrect, precisely because this is a time varying parameter that I don't observe. And so one has to be sure that that initialization error somehow vanishes or becomes irrelevant. It doesn't matter in the end. And invertibility are kind of contraction conditions, kind of for fading memory, like one does in autoregressive models, that ensure that precisely that memory of the initialization of beta 1, of the first beta, that memory vanishes, and we don't have issues with it at a later stage. We don't create a fundamental bias here. Right, so typically you need a contraction condition. So this is essentially like in an AR1 model, saying that your parameter rho, say, must be smaller than 1 in absolute value. The conditions that we associate with stationarity, there are also stability conditions, there are fading memory conditions. So essentially what we're doing here, invertibility and stationarity are not necessarily, and well, they're not the same thing. Filter invertibility is really about, again, forgetting that beta 1, that's what we're after, that initialization term. But the contraction conditions are all kind of intuitively similar, and we need some moment condition at the start. So when I set my beta 1 hat, I have a log moment condition that's very weak, and then if there's some contraction condition that ensures fading memory, I ensure that my filter converges to some limit filter, some limit sequence that does not depend on that initialization, on that initial beta hat 1. And this holds as t goes to infinity and for any parameter value, essentially. That's how these conditions are written, because they're written supremum over theta. So regardless of the parameter values, this will be ensured across the parameter space. That's the idea. And right, so if you would initialize your filter at different points with different beta 1s, right? A filter that is invertible, and then you look at the differences, right? I start my filter at a beta 1, at a different beta 1, at many different beta 1s. And I look at the difference between these filters. It vanishes very quickly if the filter is invertible. If it's not invertible, that's the image on the right, then that small difference at the start could not vanish, could even increase, could propagate indefinitely. And so a non-invertible filter would have this problem that different starting points would lead to bad outcomes. Whereas if the filter is invertible, those different starting points don't really matter. Because if I look at the difference between the filters with different starting points, those differences vanish very quickly, though. So we forget about that error quite quickly, essentially. And well, for our Gaussian case, these are essentially the contraction conditions that we're looking at. They impose some restrictions on the parameters. And if those restrictions are imposed, the filter is invertible, and then we feel at ease that everything is working well. To prove consistency and asymptotic normality of the MLE, we also typically need moments for the data and the filter. So beta hat is now a bit of also a stochastic element, right? Like a random variable that is plugged into the likelihood function. So it needs some moments. We have some generalistic moment conditions to ensure that our beta t has the number of moments that we want. I must say, for our Gaussian filter, making sure that those moment conditions hold requires a bit of restrictive conditions on X and the data, but all right. If those conditions would hold, right? If we get all of these invertibility restrictions, conditions for stationarity and ergodicity, and conditions for moments to all be satisfied. Then we get that our maximum likelihood estimator of the second stage regression is consistent, right? So that second stage regression has a number of parameters. It depends on pi hat from the first stage regression. And we also have that dependence on the initialization of the filter. Well, if everything I said is fine, then we converge to the limit theta 0 as we want, regardless of the initialization. And here t is the sample size. T star is just the sample size that we use to estimate pi, but in most applications it would be the same. Once the MLE is, once we get consistency of the MLE, one can then also show that you get consistency of the filtered path, the beta t that we're trying to filter in the first place, right? So if pi hat t is converging, theta hat t is converging, we're forgetting about the initialization beta hat 1. So they're all of these are consistent and the error at the start is forgotten. Then we do converge to the right time varying parameter, say that we're after, the beta 0 t, let's call it. So this is a bit of the theory that we have in the paper, but it's not after handling terms like pi hat t, that is definitely specific here to the IVKs, and we don't find in other score filters, in other score models. But after handling, say, the two-step regression and the specifics of IV, the theory is just a standard one: invertibility, moments, and consistency of MLE and consistency of the filter, essentially, or convergence of the filter to this correct limit sequence of beta 0 t's, essentially. Right, so that is, I'm not sure if anyone has any questions about the theory at this stage. Okay, if no one has questions, I'll just go on. It was either too obvious or maybe not obvious at all. But yeah, as I said, it's kind of standard. It's probably both. Those that are not familiar with the theory, it seems a bit abstract. Those that are familiar with score theory, it seems just the usual stuff. So maybe that justifies the no questions whatsoever. Simulation study. Right, then in practice, there's a bit of the question of how well does it work on a reasonable sample size? Reasonable, of course, being a relative term. But here we tried a few DGPs where we have endogeneity, right? And where we wanted to compare mostly kind of what happens to the usual score filter. So what if you ignore the endogeneity part and you just apply your usual score filter without doing this two-step IV type approach? And what happens if you do apply, well, these steps that we just recommended before? And well, we have some simulation results. So blue line here is the true time varying beta. And first thing to notice is that if you would do just IV, right? So if you ignore the time variation in the parameter, just do IV, well, at least you'll get that average right? So this is also not surprising. It's a misspecified model, but you expect your MLE essentially to converge to the average parameter value. It's not difficult to show. So, right, if you do two-stage least squares IV type solution, you would get the average path. Of course, that is just inconvenient when time variation is of importance, time variation in the parameter. If you would do simple OLS, you get this red line here. So you just, you get a bias, right? So instead of getting that value around 2, you actually get a negative value for your parameter estimate. So, right, the simulation here is built in such a way where actually, if you don't take into account the endogeneity, it's not just that your beta slightly off. No, you arrive at the exact incorrect conclusion. You think that X and Y are negatively related when in fact they're positively related. But okay, maybe second thing to note is that if you do score filtering without our IV approach, you would get a time varying parameter, yes, but precisely centered around, like fluctuating around that incorrect OLS beta. In some sense, also not surprising if one thinks about it. But, well, most importantly, we get to actually capture the correct time varying parameter if we do both time varying filter, score filter, and apply our IV filtering equation as we just described. So this is actually our yellow filter here on top of the blue line, so on top of the true path. Whereas this is the, say, the score filter here in yellow, far away from the blue path. Now you could argue, well, it's far, yes, but far in a specific way. Kind of, it seems only to be shifted. Well, there's a bit of both, right? A bit of both, because it's also the fluctuation is less, because it's just an incorrect parameter. So if you do the scatter of true beta versus IV score, so this is our filter, right? You essentially get it more or less well centered there, but this was an estimate, so it cannot be perfectly centered. But if you do just a score filter, not only you're off in level, you're also a bit off in slope, right? So actually the variation is more contained than the true variation. So it's both a shift and a, say, a multiplication effect there. Right, and we then, in the paper also contain a number of other simulations. What if the data is non-stationary, for example, with a break, and there it is on the lower left, it still works. That's essentially the message. And the other one still doesn't work for the same reason, essentially. What if the instrument is not so good, right? You make it polluted with a lot of noise. Well, then it doesn't work so well. That's precisely what the graph here on the left shows, also not surprising. What if you have a lot of outliers? Well, then naturally your filter will try to be conservative, and then you're well-centered, but not really capturing all of the variation. So yellow is the filter, again, blue line is the true time varying parameter. So yeah, you kind of, everything that is seen here is as one would expect. I don't think there's any big surprises. In your standard case, indeed, the whole thing is that by doing this, the MLE estimates of the maximum likelihood estimates of the parameters in the time varying update are well centered if you do the IV score, but they're just not well centered. The MLE is not, has a bias if you just do standard score. This is here for omega, for alpha, so that's the intercept. This is the parameter that multiplies with the score term, if you remember. This is gamma, that kind of autoregressive parameter on the beta. And this is the variance in the innovation term. But kind of, they're all quite far off with the score model because you're not correcting for endogeneity. Simple as that. I'll just go ahead and jump on the applications unless someone has a very pressing question. We continue. And all right, so 2 applications. Essentially, we're looking at the consumption function. Right, there's earlier research before this linked essentially consumption to in the permanent income hypothesis, right? To your expectations of permanent income. Campbell and Mankiw already a long time ago, and well, try to explain why actually changes in consumption seem to be correlated with changes in income. In a sense, consumption is too reactive on short-term fluctuations of YT, and they propose kind of a model of this type. Well, this is, it's a very incomplete model in a statistical sense because there's a lot of stuff missing here. Also, there's simultaneity because consumption depends on income, income depends on consumption in a macroeconomic sense, right? These things are all related. But et al. Enriches things a little bit, adds a bit of dynamics because otherwise these things are so misspecified that bit difficult to go through this, but also introduces a time varying lambda t. There's more papers in between. I'm just giving here a quick reference, and we take this and twist it a bit and filter lambda t, right? I think Campbell and Mankiw are essentially kind of looking at why is it that these short-term variations in YT determine so much of income. Changes in income when it shouldn't, right? It should be looking at long-term income expectations. But actually, what turns out is that when they did this, that was the case. But over time, that relationship has disappeared, and thus the time variation in lambda being relevant, right? So the model we fit is this one, very similar, but we add then their recession cycles just to capture a bit of how expectations change, kind of trying to capture here that permanent income, how expectations change when you're a recession or outside of a recession. We could for sure enrich this a lot, but just something that gets us going to filter that lambda. So this is changes in consumption. That's disposable income in Y. This is an N-bear recession indicator. And we're interested just in filtering lambda. Again, endogeneity is an issue because of simultaneity and a number of other things. This is the data that we have in front of us, the changes in consumption and disposable income. The instrument we use, I think I've mentioned here, are the 1 period ahead Green Book forecasts of changes in real disposable income. And by being 1 period ahead forecast, they kind of qualify as an instrument. There's a lot of discussion about the quality of such instruments, but okay, we use this here as an instrument, and well, we estimate our filter. This is the OLS regression estimate, the IV regression estimate, which already lowers the lambda, the estimate of the lambda parameter, and these are the estimates of the score model and our IV score model. And I think what is interesting is to arrive here at this graph. So if you would do a score filter, you would tend to overestimate this relationship between consumption and income. So not only it used to be much higher in the past, but also by not taking into account endogeneity into account, you might be led to assume that this is still present. What we're saying is actually if you take into account the endogeneity, so not only the time variation in the parameter, but the endogeneity as well, the conclusion is essentially that that relationship between changes in consumption and short-term changes in disposable income, which Campbell and Mankiw were worried about before, it's actually no longer there. If you do IV filtering, you're essentially zero nowadays. This is not, with bounds, you contain the zero very easily, and there's just no relationship anymore. If you don't do IV score, you might still be led to think, I'm zooming in here on the last number of years, you might be still led to think that a weaker relationship is still present. But if you do IV score, then it just disappeared. So the old concerns are no longer relevant. And this is just a quick comparison between score and IV score here. And I will quickly switch, if there are no questions, to the last application on the Fulton fish market. So a well-known application used already in a number of papers as well, related to, again, the original application of IV almost 100 years ago, because it's related to estimating supply and demand equations, supply and demand functions. And right, so we have a market where prices and quantities sold are recorded in each period. One is interested, suppose, in the slope of the demand equation, so the evolution of price elasticity of demand, and how it can change over time. However, there is endogeneity, right? Because both prices and quantities are determined jointly in equilibrium, essentially. And right, others have investigated this data set before. The instrument that is used is how stormy weather conditions were at sea level the day before, a bit as an instrument, because, well, it can account for shifts in the supply curve without affecting demand. It can account for shifts in supply as it determines the fish catch without affecting demand. And, well, we applied to that data set, score and no score. And, well, there is, we have a time-varying filter, a time-varying result for the IV score, so a demand function with a time-varying slope, essentially, and where we get to correct for the endogeneity issue, as others have done already. They just didn't do it in the time-varying setup, which we use here, essentially as an illustration. Well, I will ask if anyone has questions. Otherwise, I will just wrap up with a few points of conclusion.
Yeah, I think we're gonna just leave questions to when we stop the recording.
Okay. Then I will wrap up and then we move to questions. So, yeah, I think the conclusion is that this type of IV score filter can offer a simple and intuitive solution for filtering time-varying parameters in the presence of endogeneity, which is, such a pervasive issue in economics and finance and business. So I'm guessing more often when we filter time-varying parameters in regression models, we will be actually applying this type of IV score filtering approach rather than a non-IV approach because of fears of endogeneity again. The filter, as we've seen both in simulations and theory and practice, seems to conveniently address endogeneity bias and has the appropriate properties. And, well, that's it in terms of conclusion. I'll leave it there, just the obvious, but thank you.
Okay, so